So, hello everyone, welcome to lecture 18. So far we have been looking at so when two species will so combine to form a solution, right. So we said there should be some driving force to form the solution, and the driving force is thermodynamically the driving force is just G mix, right. So when they form a solution, how much does the G, the small g, right, so reduce compared to when they are isolated species, right. So when they are isolated components, component 1 and 2, right. So compared to when they are pure versus compared to when they mix and then contaminate each other by forming a solution, what is the free energy difference that I get, right. So and if that free energy difference is negative, then I have a driving force that is positive, so that can form a solution, okay. And then we said that so we introduced the idea of this G mix is of course dependent on mu 1 and mu 2, right. So in that phase, so mu of component 1 in alpha, mu of component 2 in alpha, and we said another proxy for mu 1s and mu 2s are activities, right. So that is where we have defined what activity is, and we said so eventually if I want to go towards a phase diagram, right. So constructing a phase diagram by changing the compositions of 1 and 2. So 1 and 2 are mixing, right, and they can stop mixing at some point, they can stop forming a solution at some point, they can just segregate out of each other, right. So I want to know at what compositions does this happen at a given temperature and pressure. So I have to look at phase diagrams essentially, right, and this phase diagram should include temperature, pressure, and the third axis will be composition, okay. And we said we have defined the language of composition. We said so we will have one variable in a binary system, right, so that x2 is my composition variable, and based on that we have arrived at a situation where we need a model that will look at the relation between the mu's, the chemical potentials, and the compositions, right, so or the activities and the compositions, right. We said the easiest, simplest model is what is called the ideal solution model, and the physical picture of ideal solution model is that if I put A and B together, put pure A and B together, just by virtue of entropy, just to maximize the entropy, they will start mixing, okay. And so this mixing or forming a random solution as it is called is in process of maximizing what is called the configurational entropy, and the configurational entropy is given as x1 ln x1 plus x2 ln x2 that we have seen times kb minus kb, okay. And we said the free energy or the driving force for mixing just comes from entropy, right. So in an ideal solution it just comes from entropic mixing, right. So this is like I put something like a coffee droplet in a huge lake. This coffee droplet will start spreading, will start mixing with the water, right. So will start contaminating more and more water, right. And the idea is essentially I'm trying to access more and more states, I'm trying to maximize my entropy, and I'm trying to maximize my configurational entropy, and that's exactly, entropy will prefer mixing, right. So that is, or people say entropy means disorder, right. So what it means is essentially it prefers mixing, and mixing in a very sort of randomized way, right. So if I leave entropy, if I leave it to entropy, if I have an alloy of A and B, right, so platinum palladium 50-50, right, so 50% platinum 50% palladium, I can take any site in the structure of platinum and palladium, and then there is a 50% chance that that site will be occupied by platinum, and there is a 50% chance that that site will be occupied by palladium. I cannot with any certainty say that this is going to be platinum, this is going to be palladium, right. So that is what a random solution is, right. So entropy will try to randomize, right. So rather than saying it is mixing, it is actually mixing in a random fashion, right. So it will try to randomize with equal probabilities, so so if I have 30% platinum, 70% palladium at every atomic position, there is 30% chance that I would find platinum, and there is 70% chance that I would find palladium. So that's a random alloy, right. So entropy would want to form random alloys, and the ideal solutions typically form random alloys, okay. So we have seen the ideal solution model where we just said that the activity is nothing but the composition, or mu is just simply given as kb t ln x1. Mu 1 is kb t ln x1, mu 2 is kb t ln x2, and based on that we have derived that the only form of advantage I get by mixing is entropic advantage. enthalpy of mixing is 0, right. And that also comes from the fact that so I have the A and B, right. So these two should bond with each other. So A, there is no way so enthalpically I cannot say that the bond energy of A and B is somehow larger, or A prefers B more than A prefers A. I cannot say that, which means AA bond energies are the same as AB bond energies, are the same as BB bond energies, right. So whether A bonds with B or whether A bonds with itself, whether B bonds with A or whether B bonds with itself, it's the same thing, right. So enthalpically I have absolutely no advantage of mixing, right. So whether I mix, whether I don't mix, I'm agnostic to it. So the delta H, the H of mixing is 0, whereas S of mixing is so entropy prefers mixing, right. So that's an ideal solution. And we said what are ideal solutions, possible ideal solutions. We gave some examples. I said there is hafnium oxide, zirconium oxide, there is uranium 235, uranium 238. They are different isotopes of the same atom. So nuclear charge wise they are different, but chemical bonding wise they are exactly the same, right. So they will mix, right. So chemistry wise they have to mix, and we are looking at chemical thermodynamics. We don't really care about the differences in the nuclear charges, or in the nuclear mass, right. So we just look at so chemically can they bond, and then U235 bonds exactly the same way to U238 as it bonds to other U235, right. So it will form a random alloy. That's an example of a completely random alloy, right. So similarly you can approximate some of these other alloys like hafnium oxide, zirconium oxide, platinum palladium, right. So all these alloys tend to behave like ideal solutions, okay. So they are like ideal solutions. We look at the phase diagrams of ideal solutions later, but then we said okay, there are some intuitive rules, right. So like material scientists and chemists, we want to actually understand some intuitive rules whether materials form ideal solutions or not. So I said hafnium oxide, zirconium oxide. Hafnium and zirconium, oxygen, so if I ignore oxygen because oxygen is common in both, hafnium and zirconium, both of them are in the same charge state. They have a charge state of 4 plus, right. So if I look at hafnium oxide and zirconium oxide, right. So hafnium is in 4 plus, zirconium is in 4 plus, right. Hafnium and 4 plus and zirconium 4 plus have almost the same ionic size. How do I know this? I go to what are called Shannon radii. I check out the Shannon radii, which are the ionic radii of hafnium and zirconium. Let me just quickly show you how I look at it. I mean there is one nice website that just gives you the Shannon radii, right. So this is the MIT website, database of ionic radii or Shannon radii. I think both are similar, okay. So now I am going to look at hafnium, right. So what is the Shannon radius of hafnium? Where is hafnium? Hafnium is 72, hafnium is here. Hafnium has a charge of 4. So the radius, the ionic radius depends on the charge and coordination number, right. So depends on how many oxygen is hafnia coordinated to, right. So hafnia has a charge of 4, that's what we saw, oxygen 2, each oxygen has 2 minus, so hafnium has a 4 plus charge, right. And the coordination number is since I'll just tell you, I know the structure of hafnium oxide, and then generally the coordination number is 7, right. So in hafnium oxide, so the ionic radius is 0.76 angstroms, okay. So remember that value. Hafnium has an ionic radius, hafnium 4 plus with a coordination number of 7 has an ionic radius of 0.76 angstroms, okay. Then what about zirconium 4 plus? Again same coordination number equal to 7 or Z, we will write it as Z, okay. So what is the Shannon radius of that? I will go back to the same website and go behind, look at zirconium, right. Zirconium 4, I am looking at coordination number of 7, 0.78, right. 0.78 angstroms. So this is 0.76 angstroms, this is 0.78 angstroms, both of them are relatively the same, right. So the radii, atomic or ionic radii are the same. Okay. The valence or the charge states are the same, or similar, right. So, similar meaning less than 15% of each other, okay. So, are the same, charge state should be the same, ionic radii are similar, not same, but similar, right. Then so if I replace hafnium with zirconium, hafnium oxide likes a particular crystal structure, likes to be in a particular crystal structure, what is called the monoclinic structure, right. If you really know something about space groups, this is what is called P21 by C. Space group, if you do not know, that is fine, right. So, you can check out my other course where I talk about space groups, and zirconium oxide also likes to be in the same crystal structure. Okay. And the fourth property, right. So, now if it turns out that zirconium oxide likes to be in a different crystal structure than hafnium oxide, then so putting hafnium in zirconium sites or zirconium in hafnium sites will make it slightly complicated, right. So, I will create some stresses and strains, because zirconium would ideally locally want to have a different crystal structure, right. So, hafnium oxide, let us say the crystal structure of hafnium oxide is hafnium oxygen, it looks something like this, right. Now, if I replace one hafnium with zirconium, right, let us say this is replaced with zirconium. Zirconium locally wants its crystal structure, right. Hafnium locally wants its crystal structure. Okay. If there is no compatibility, if zirconium prefers some hexagonal crystal structure and hafnium prefers some monoclinic crystal structure, if there is no compatibility, they will strain each other, right. So, zirconium zirconium wants to be tall, but hafnium wants to be nice and symmetric, right. So, let us say that is the property of the crystal structure, zirconium wants to be tall and thin, but hafnium wants to be nice and symmetric, right. So, short and symmetric in both in all the three directions, right? That is the nature of the crystal structure or nature of the unit cell, right. Then putting both of them together, right. So, this guy will apply strain on this guy will apply stress on this guy, right. So, there are some internal stresses that develop, and so as a result that is not good for mixing, right. So, it is like I have two people living in the same house, if they have the same attitudes, so if everything is compatible with each other, that is good. But so if one person loves to watch movies, the other person does not hates to watch movies, right, then they put strain on each other, right. So, and so this person will say, oh yeah, why are you watching movies with such a loud volume, and the other person will say, no, it is not loud volume, I am generally watching movies, why do you hate me, right. So, there is bound to be friction, and they will not mix, they will not form a solution. So, it is better that those roommates separate out, right. So that's essentially what this is saying, right. So, if I am in different crystal structures, if I prefer to have different crystal structures in bulk, then mixing will become difficult. Turns out that in case of hafnium oxide and zirconium oxide, the crystal structure is the same, so they will mix, right. So, so they prefer to be in the same crystal structure in bulk, so mixing becomes easier. So, their ionic radii are the same, their atomic charges their valence states, or so the oxidation states are the same, 4+ for both of them, they are going to crystallize in the same crystal structure, and there is another property that their electronegativities are the same. Right. Now, if these constraints, these four principles that are countable on your fingers, right, are satisfied, then those two species A and B, right. So, A and B are 1 and 2, can form ideal solutions. Okay. So, so ideal solutions do exist. For example, I gave you the example of hafnium oxide, zirconium oxide, but something like platinum, palladium also forms an ideal solution. We will look at the phase diagrams of ideal solutions very soon, but so ideal solutions do exist. It is not just a theoretical construct that I am telling you. Okay. So, these are the so called what are called the Hume-Rothery rules, okay, which I asked you to do some self study in the last class, and in this class I am actually telling you what these rules are. Okay. All right. Now, that is an ideal solution, and ideal solution is the simplest of the solution models, right. Now, let us so in an ideal solution we said G, right. So, which is given as G mix, right. So, which is given as G of the solution minus G of unmixed compounds, right. So, that is x 1 G 1 plus x 2 G 2, right. So, these are G of the pure compounds, or G tilde, G 1 tilde, G 2 tilde, right. Sorry, we wrote G 1, I mean I am just not to mess up the notation, we wrote this as mu 1 tilde plus x 2 mu 2 tilde, right. So, that is G mix, right, and this G mix so G ideal mix comes when mu 1 of x 1 is just k t ln x 1 and mu 2 sorry this is dependent on x 2, this is dependent on x 2 again, k t ln x 2, right. So, this is an ideal solution, right, and in an ideal solution we sort of said that G ideal mix is nothing but k t times S ideal mix, everything comes from entropic mixing, right. The enthalpic mixing H ideal mix is 0, and that is illustrated by the fact that epsilon A A equal to epsilon B B equal to epsilon A B, right. So, it does not give me any advantage in mixing or not mixing, right. So, enthalpically there is no advantage, entropically there is an advantage in mixing. So, ideal solutions do mix with each other. Okay. Now, so let us go to the next slightly more complex model, but next simple model, right. Now, I am looking at G mix as H mix plus so T times S mix, right. So, I can write it as this. So, in the simplest model H mix is 0, right. So, in ideal solution H mix is 0, okay, and only S mix exists. Now, we are going to put some H mix, right. So, in the next model H mix, so in what I am going to call it as a regular solution model, turns out that H mix is not 0. Okay. So, what is H mix, right. So, now let us define another quantity just to confuse you even more. I am going to define another quantity called G excess, right. So, what are called the excess quantities, right, and the way I define this excess quantities is I am going to look at my solution and I am always going to compare it with the ideal solution. Okay. So, now how much is my G more or less compared to the ideal solution, those are what are called the excess quantities. Similarly, I can define H excess, H excess is H of the mix or H of the solution minus H of the ideal solution, right, and H of the ideal solution is anyway 0, correct. Similarly, S excess also can be defined as S of the mix minus S of the ideal solution, right. So, I can define what are called the excess quantities. Okay. Now, in case of a regular solution, just bear with me, I am just going to give you the model first and then try to understand it physically and try to so we can try to understand that the physical meaning of this model later. I am going to say that G excess, right, is equal to so and G excess is dependent on x 2 t and p, let us not forget what it depends on, is equal to some factor, some interaction parameter called omega times x1 times x2. Now, x1 is the composition of 1, x2 is the composition of 2, and they are related, right. So, x1 equal to 1 minus x2. Okay. Okay. Now, this is just so how I define what is called a regular solution, a simple model. Okay. So, first let me define it mathematically before going to looking at what this omega is, right. So, omega is what is called the interaction parameter. Okay. Before looking at the physics of it, let us just mathematically define Gxs is equal to omega times x1 x2. Okay. Now, if Gxs is that, right. So, we can then what is G mix, right. So, G mix is G excess plus G ideal mix, right, and G ideal mix I know is just entropic in nature. So, KBT times x1 ln x1 plus x2 ln x2, right. So, this is the entropy of mixing that. So, entropy of mixing is ideal, right, and Gxs is omega x1 x2, right. So, this is the total G mix, right. So, what is the total driving force I have to mix, right. So, that is n times G, but negative of this will give me the delta G, which is the driving force is minus n times G mix, right. So, this we have seen. Okay. So, the driving force for mixing or for forming a solution is omega x1 x2 now plus kT x1 ln x1 plus x2 ln x2. Okay. So, this is the new driving force that we have. Okay. Now, I can then estimate what mu1 is from G, right, as a function of x2 and mu2 as a function of x2, and so mu1 and mu2 are going to be just mu1 pure mu1 plus kBT ln x1. This is just the ideal solution ka mu1 also is the same thing, plus there is an omega x2 square. You can do the tangent construction, right. So, I told you how to get mu1 x2 and mu2 x2 from G as a function of, or G mix as a function of x2. Okay. So, this we said from G mix you have to get G, right. So, from G mix you have to add the G equal to G mix plus x1 mu1 tilde plus x2 mu2 tilde. Right. From this expression I can get what mu1 x2 is and mu2 x2 is, and they turn out to be very simple, right. So, this is nothing but mu2 tilde plus kBT ln x1 plus omega x1 square. Okay. Now, remember that so when we did ideal solutions, until this part is just ideal, right. So, even even when I write mu1, I should not be using this color because it does not show up pretty well. Okay, so let me use blue. So, even when I do mu1 and mu2, right. So, I have some ideal component. So, mu1 of x2 is equal to mu1 ideal of x2 plus omega x2 square, right. So, I can just say mu1 excess is equal to omega x2 square and mu2 excess, right, is equal to omega x1 square, right. So, I can so this is the excess compared to the ideal solution, right. Okay. So, we have defined, what did we define activity as, right. So, activity has been defined so mu mix, right. So, we have defined activity from mu mix. Just go back, I mean, so if this is confusing you, don't worry, just go back and look at this nomenclature again. Mu mix, right. So, this is the partial this is the chemical potential of 1, right, in the mixture, right. Sorry, chemical potential of 1 compared to the chemical potential of pure compound, right. So, chemical potential of 1 in the mixture or in the solution minus the minus mu1 tilde, that is mu1 minus mu1 tilde, right. So, mu1 x2 minus mu1 tilde, right. So, this is the mu1 mix, right. So, just like G mix I have a mu1 mix, right. Now, we said mu1 mix from the definition of activity we said this should be equal to kBT ln A1, right. Similarly, mu2 mix x2 equal to kBT ln A2, right. Now, what is mu1 x2? Mu1 mix x2 is so that is mu1 mix x2 equal to mu1 xs plus mu1 ideal, right. So, that is how I actually define the xs, right. So, now mu1 xs I know is omega x2 square plus mu1 ideal is kbt ln x1, right. So, I am actually looking for a relation between mu's and x1s, right. So, and g's and x1s. So, this is I already have a relation. Similarly, mu2 mix x2 is equal to omega x1 square plus kbt ln x2. Okay. So, these are my relations from mu1 xs, so I get these relations. Okay. Now, I am going to define another quantity, right. So, I said mu1 mix is kbt ln A1, right. Now, A1 itself I am going to say is related to what is called the activity coefficient gamma 1 times x1, right. So, similarly, A2 is the activity coefficient gamma 2 times x2. Right. So, it is A1 and A2 are somehow so this related to the compositions. I am just going to define they are related to the composition through what is called an activity coefficient, right. This is also an activity coefficient of 2. Okay. Now, we will try to look at what activity is based on the activity coefficient, that is where we are getting it. But bear with me again. So, what do we have here? Yes. So, now I am going to write mu1 mix equal to kbt ln gamma 1 A1, and that is equal to omega x2 square plus kbt ln x1, right. So, from here I know something about gamma 1 is equal to e power omega x2 square by kbt, okay, and gamma 2 equal to e power omega x1 square by kbt, right. So, activity coefficients are actually related to your interaction parameter, right. So, omega is what is called the interaction parameter, right. Now, why is it called an interaction parameter? So, essentially if I have so in some vague way, right. So, if A and B are so earlier in the ideal solution case A and B are agnostic to each other. A can mix with B or A does not need to mix with B. A can form a bond with A can form a bond with B, or A can form a bond B can form a bond with B, right. Now, A and B, how are they interacting and how is that interaction different from AA and ABB? That defines what interaction parameter is. Interaction parameter tells us the difference in bonding or interaction between AB and AA and BB. Okay. All right. So, okay. So we have vaguely tried to say what omega is. Omega is the interaction parameter, and interaction parameter tells us the difference in bonding between AB, AA and BB, right. Now, and so if I know the interaction parameter, right, if there is a difference in bonding, omega is 0 in case of an ideal solution, right. Omega should be 0 for ideal solution. So, there is no bonding difference between AB, AA and BB, right, but omega is non-zero for a regular solution. So, there is some interaction between AB which is different from AA and BB, right, and this difference in interaction gives me activity coefficients, right. If the interactions, if omega is non-zero, that is A and B are bonding differently or their bond energy is different compared to AA and BB, right. A likes B more or A likes B less compared to itself, or B likes A more or B likes B likes A more or less compared to itself, right. So, then an interaction parameter arises which is a non-zero quantity, then my activities are not the same as compositions, right. So, then activities so are differ from compositions, and so I have, and they differ from compositions using an activity coefficient, right. So, activity coefficient is this gamma I, right. Now, if there are too many interactions, if my solid so if platinum and palladium are bonding differently, or they have much stronger attraction compared to platinum and platinum, if I am not saying it is, but if that is the case, then my activities and compositions are quite different, and they differ by what they are related by what are called activity coefficients, and in the activity coefficient you have the interaction parameter. The interaction parameter relates the activity coefficient and composition. Okay. So, atomistically you can think of it this way. What is the idea of activity coefficient and activity in general? For an ideal solution, however, it does not matter, right. So, looking at these equations, you can say that for an ideal solution, AB is the same as AA is the same as BB, the bonding is similar. So, for an ideal solution, interaction parameter is 0, right. So, the bonding is similar, and so activity and composition can be used in sort of a very so they are one and the same. Okay. But for a non-ideal solution, they are not the same. Okay. So, now let us calculate what this so I have Gxs is equal to omega x1 x2. From this, let me calculate what Sxs is. Sxs is nothing but dou Gxs by dou T, and that is 0, right. So, I do not have any Sxs, right. So, in a regular solution, the assumption is omega is not a function of temperature, x1 and x2 are also independent of temperature. Omega x1 x2 are all independent of temperature. It is an assumption, it need not be true, but it is an assumption of temperature. Okay. In a regular solution, Sxs is equal to 0, which means S is nothing but S ideal mix, okay, and that is just kBT ln x1 ln x1 plus x2 ln x2. Okay. So, the entropic mixing is still ideal in nature. So, entropy still prefers ideal mixing and randomization, right, whereas enthalpy, let us calculate what Hxs is. Hxs is, we said this formula dou Gxs by T, right. So, by dou 1 by T, right. So, you can check out this formula. Now, this turns out to be so this is just dou omega x1 x2 by T by dou 1 by T, right. So, omega x1 x2 itself is not dependent on T, and that is just omega x1 x2, right. So, Hxs is the same as Gxs, right. So, all the excess free energy is coming from enthalpy term, not the entropy term. So, in a regular solution, all the excess free energy is enthalpic, right. Entropy is just ideal mixing, right. So, entropy, so right. So, entropy still looks like an ideal solution entropy, but all the excess free energy, not the mix, not H mix, right. So, Hxs is the same as Gxs, right. So, now that we have established this, all the excess free energy in a regular solution, right. So, regular solution is different from an ideal solution in that I have added some excess enthalpy, right. So, regular solution is different from an ideal solution by Hxs, right, and Hxs which is equal to Gxs, that is nothing but omega x1 x2, right. So, we will stop here, but in the next class we will start by actually looking at the atomistic details of what this interaction parameter is, right. So, I said somehow it should reflect the bonding differences between bonding A with A and A with B, right. So, we will go back to our fundamental causal crystal, and we will see what this bonding difference is, and we will see the enthalpy Hxs. We will try to estimate what this Hxs is in a very statistical, so just by counting the bond energies, right, and then actually show that this omega is indeed related to the differences in these bond energies. Okay. So that we'll start with that in the next class and try to understand the intuitive or atomistic understanding of what this omega is, right. And then so we have an enthalpic term, right, coming because of differences in bonding. We have an entropic term. Entropic term always prefers mixing. Enthalpic term, we do not know what it does yet, right. So, we will see that, right. Now, and then we will mix both of them, we will combine entropic and enthalpic terms, and then we will try to say what wins, right. So, do these A and B, do they really want to mix, do they really want to segregate, right, or do they want to mix in a particular fashion, right, not random mixing. Entropic mixing is random. Do they want to mix not in a random fashion, but in some kind of an ordered fashion, right. So, we will discuss all these ideas in the next class. Okay. So, with that thank you for this class, and then so we will meet you again in the next class.